Oops, that's pretty good.
Is the lighting good?
I think so.
So this is our crude version of the Veactor for Verde.
What do you call this?
Veactor?
That's V-E-A-C-T-O-R.
And the reason we call it a Veactor is because it's a hybrid between a transformer and a reactor, and what it does is it reacts to the load we connect to it. Whereas a standard transformer is a fixed ratio device.
Right.
This is not a fixed ratio device. This is able to change without any circuitry. So it's a new twist on the physics of a transformer, not just a transformer. There's no solid state components.
So instead of a conventional primary coil, secondary coil, fixed number of turns on the first one, fixed number of turn on the secondary coil, yours is adaptive. Right?
Yeah. With by the magnet adapts by the magnetic field. So I'll show you this. This is a standard 120 volt bulb. It's a standard 120 volt bulb. Okay. Taking a hook up this side to the bulb. This is wired as an isolation transformer, which you'll see in a minute here. So it has the same amount of windings on the primary as the secondary. But yet I'm going to do something that an isolation transformer can't do. So this is just a strip of LEDs with no diodes on it. It's just LEDs, and it's a 12 volt strip. So
It's DC.
sure. LEDs are all LEDs at DC. So watch. I can run the strip and I can run the light. Now, just to show you that this is not a 12 volt side and that's not a 120 volt side, I'll turn it around. To show you that this device is actually adapting to the load. That way these clips are squashed.
This is what you're referring to, like that.
Yeah. Now, it shouldn't be able to power a DC device, and I should burn that thing up.
Yes.
And I certainly shouldn't be able to turn these things around. You can say, well, there's two secondaries. No, there's really just adaptive
You would not be able to turn that on, you would be blowing up this.
Yeah, I should blow that up right now. But you'll see. Oops, let me hook this up the right way. Okay, how did I do this now? Oh, my clip leads went bad.
It's okay.
So you're getting directly AC to this?
It's adapting to what the load is. So what it does is, this thing puts out a sine wave, but the sine wave is able to collapse the magnetic field. So in other words, this diode only wants to see half the sine wave,
Yes.
DC. And this will take both. And then this only takes 12 volts. So after 12 volts, it collapses on that side. And when it's on this side, it collapses.
Is this particular ratio now is set for a 12 volt DC?
No. You
It
see,
can
I can go either way. So the ratio is set to put out 120 volts. See, I can do 120 volts here. Here, I could do it the other way around. Now, the interesting thing is this. I can also do this. Got another strip here.
Yeah, I'll bring you one.
I can put two 12 volts on there, which really shouldn't be able to do. This is another 12 volt strip.
Now that's interesting. I think the clips
One of these wires is bad. Yeah. You see how bright it is. Now here's the interesting thing. Did you hear how loud that hum was?
Yeah.
Watch. That's the magnetic field reacting to the load, the polarity of the load. Watch now. See the difference in humming?
Yeah.
Another thing it does is, you should burn those LEDs out. It's enough to power this, it should burn that out.
After it should blow it up immediately.
Yeah, so it adapts to the load. So that's why we call it a reactor, because it reacts to the load. So the advantage of this is that because it's not a fixed ratio device, you don't get the heat generated on a standard transformer, because it only supplies as much power, for example, as much power as this can take, as much power as this can take. So this is the upper limit, this is the lower limit. So the end result of being an adaptive device is you don't generate any necessary heat. No bucking in the transformer.
So your efficiency, that's part of efficiency, because part of we're getting from AC to DC is a lot of energy loss there. And
going
that's
from 120 volts to 12
converted to
volts.
heat. And you say because of this adaptive, it doesn't have to really use all this massive stuff. It uses as needed.
Right.
Is that correct statement?
Yeah. So you get the idea. It's an efficient type of device because you don't need all the solid state circuitry. You don't need the regulators. You don't need the rectifiers. It does it all with the magnetic field.
In this particular demonstration, how much current the DC 12 volt DC providing? This particular.
This thing will provide up to 5 amps. So it'll provide as much as a. Here's what's really interesting. I found out the hard way. Somebody explained it to me, and I didn't know it at first until somebody explained it to me. When they make diodes, they make the die for the diodes. Okay, then they cut out all the individual diodes. Well, they're never consistent in voltage, which means some of these diodes may come out most efficient at 9 volts, most efficient at 20 volts. They all come out different in the die. So what they do is they test them, and they test the ones that'll give you the optimum amount of light voltage at the certain voltage they're constructing, which means they don't put any 9 volt ones on here. He's going to burn them out.
Sure.
So what I found out was diodes like to be flickered. They like to flicker the best. Because when they start generating heat, they get less efficient. So flickering happens at a very, very fast rate with this device. Because this is going through the sine wave.
It's just on and off, but
Yeah.
Your eyes cannot
So
distinguish.
it comes brighter. It makes it. So if you put a light meter on this, it takes 1/3 the energy to light this to the optimum light as it does with straight DC out of a switch power supply. Because you're getting a little bit of flicker, you're allowing the die to cool down in between flicker, and you're not bucking the transformer, and you don't have the regulation, you don't have the rectification, because a standard switching supply supplies power to a capacitor bank, and it keeps the capacitor bank charged for when you need the power. None of that happens on this. If there's nothing plugged in here, I'll show you another interesting experiment. These broken, so I'll put them over here. We'll hook this up to here. Now I'll show you something really interesting that you won't understand until I explain it to you.
A little louder.
Okay, there's the power to the LEDs. Now when I hook this up, you'll see this will run off of this side. Okay. Okay. Now there's 120 volts there. Okay, but here's the interesting thing.
I know. I was gonna ask you.
You see me touching it.
I know. That's why I was so. I was keep looking at the LED.
I touch it?
Yeah, there's a little bit of voltage, but not much there.
Okay.
Not
But
if you
you
touch
can't-
this socket, you'd get a shock.
Of course.
So, but look,
That's why I was so worried. Keep looking
Yeah,
at your
I mean, you were
fingers
just
and that.
manipulating all
I was
these
saying,
things.
should I say something? Should I
And
not
you
say
can't-
something?
If
Oh
you
my
short
God.
this thing out,
okay. If I short it out, all the power's going to go to that side.
okay.
See? But look,
That's good.
that's pretty cool.
That's pretty cool.
What's that to the GFIs? Right.
So,
if
What's
you
the,
adapt
what's
this
the
to
GFI?
ground fault in the
Ground
road.
faulting.
So if you
It's not
adapt
a-
this to the power line industry, all of a sudden it makes power lines very
So
safe.
is that true?
Automatically balances the power lines.
I don't want to change the subject. Is that true that you could have a landscaping lights, Malibu lights,
Yeah.
provide AC, and you
Yeah.
provide
And they can be DC.
you provide
LEDs.
DC without if this is in the ground and it gets wet,
So what?
nobody's gonna get electrocuted.
Nobody.
Correct?
Correct.
Right. So you can put this at your fuse box and provide the wire out to the LEDs. And it'd be safe. Totally safe. So here's the other application. You can hang two grids off of this. Grid A and grid B, and they're all automatically going to balance.
It's a lot of aeronautics application.
It's tremendous applications. The
And
military,
also
the
automobile.
military has a big problem with generators, syncing
Yes.
generators. Think about this thing in reverse. You put a generator here and you put a generator here, and this one's automatically synchronized. Nobody can do that because they have a big problem with the sync reverters. Sync reverters have always been a challenge. How do you sync these two generators? Well, because these things are automatically synced with the primary, you don't have the problem with the sync converter. So the applications go on and on and on and on for this thing. I mean, many things you can think of. But this is the really cool part that I like to show people.
Yes, that's the coolest part.
Yeah.
That's what I was.
Not
I was.
flipping
I was worried when you were playing with that thing. His hands are too close to those wires. But
Yeah, I'm doing that on
I
purpose.
didn't want.
Yeah.
Go all
No,
around.
how? I mean, this $100 million question. How make it this possible?
Well,
I mean,
you got a primary, and the primary creates a magnetic field that goes around this way and goes around that way, like a figure eight, like two donuts.
Right.
Okay, so they're both magnetically coupled. Okay, so now when this one is coupled to this LED, there's a certain amount of flux that goes through there. As soon as this one shorts out or collapses, it has another place to go. It has a dual magnetic path. So it goes to this side. So that's how it happens. The magnetic field is able to collapse very easily. So it's built like a seesaw. It's got two sides of the seesaw. And the two sides stay balanced until something changes on the other side and the flux goes the other way. So the flux has a dual path. That's why it's not a fixed ratio device. In other words, you generate a certain amount of flux here, but it has two places to go, two possibilities. That's why the flux can collapse when you hook up a 12-volt device, or you get all the flux when you hook up a 120-volt device. But when I hook myself up to it, I don't get a shock, because all the flux is on the other side. I'm not drawing the flux out of it. And if I wet my fingers, I'll feel more of a shock. But it's not dangerous shock. It's not a direct connection like this is. I touch this, I'm going to take a pretty good damn jolt. Yeah. But if I can power a light bulb and still touch it, man, that's a hell of a safety product alone.
That's
tremendous. I mean, look, think of the marine applications for this.
Yes.
When they hook boats up to the marinas, and huge benefit there.
Child safety.
Child safety, yeah.
Yeah.
So just about every place you can think of where power is coupled in this way.
Yeah, well, what I see in here, you'll be able to, one is safety. The other one that is really important in here, the heat.
Yeah.
Right?
But heat is such a small, part of this is efficiency, because there's so many other benefits.
Because if you have this one going continuously, like conventional transformer, right?
Yeah.
That one is always on, right?
Yeah.
And generating DC and always on and produce heat. For example, if I take this device, what you have, and I have that light bulb sitting there for 1 hour, right?
Yeah.
And energy consumption going through there, and the heat with your invention here versus a conventional method.
Yeah.
Will you be able to really quantify that? What's the benefits are? I mean, as far as is a heat and also electricity consumption.
Yeah.
Have you had that thing?
Yes, it's really difficult though to come up with an efficiency number. And the reason is because this doesn't put out a standard sine wave. So if you try all the new meters they have out that measure efficiency, they all do sampling. But they sample on an expected sine wave. So it's really hard to measure the efficiency of this, because this thing's always varying with this load and with that load. As that filament heats up, there's all kinds of different efficiency readings. So it's hard to take an efficiency reading, but evidence of efficiency is absence of heat. And the fact that you can see that you got a 12-volt load to a 120-volt load, this thing's not supplying any more power than it's needed. So it's automatically, it tells you it's got to be as efficient as possible. It's a no-brainer. You can test that in your brain. You don't need a piece of equipment. If I can go from 120 volts to 12 volts, that means this thing doesn't supply any more energy than is needed. That's a no-brainer. I don't even have to test.
How much gas do you produce?
About 19,000.
19,000?
Yeah.
And how can you further miniaturize this?
Yeah. The only reason we make it big and clunky like that is because we want to make worst case.
Okay.
So we made the worst, most inefficient device we can possibly make on our bench.
I see. And in terms
it's only going to get better.
In terms of number of factors, how small you can go?
As small as a transformer company can build a transformer, because It's a standard transformer with a new twist.
I see.
We can put it in the small plug-in
We could even go to chip
transformers.
level. If we had to, we could go to chip
You
level.
can go to up to chip level.
We have it.
You can do it, with the amount of magnetic field and all of that. You're still going to comply
Yeah.
with
Yeah.
your physics.
What I did was I took the physics of this Veactor device, and I went to a local transformer company. I said, "Show me how you make a transformer,"
Yeah.
because it was nice to have this idea worked out, and I did have an early prototype, but it was very expensive. It was $200, and everything had to be custom manufactured. I don't know if I ever showed it to you.
Yeah.
You have that one floating around there?
The original?
Yeah, the blue one. It was very expensive to build, and I said, "There's got to be a cheaper way to do this." So I took it to the transformer guys, and I gave them the spec for this, and I could never get the right one to turn out. I could never get it to turn out the right way, and I couldn't understand why. If I'm building it, why can't they build it? And I couldn't understand why they couldn't build it. So I said, the guy, this is it here. This is our early prototype that works. Very expensive to build, though, because every piece is built exactly what it should be. So we had to have custom cut laminations, and the cores are custom, and everything is just custom on that. So
What's
it's a
the difference
transformer.
between this and that?
Well, this is manufacturable with standard materials. This is all custom materials.
Okay, to custom.
So this is engineered right to the specification, materials and
Right.
specification. We took this and I modified it into this. So what I did with the transformer company was, I said, the guy's name is David. I said, "David, hand step me through the process like I'm an idiot, okay? Spoon feed me how you build a transformer, and I'll figure out how I'm doing it here." He says, "Okay." So we take a piece of software and we punch in all you. I said, "Well, no, wait a minute. Go backwards and tell me how you used to do it before you had the software." "Oh, okay." He says, "Well, he goes in the other room and I get my information." He goes in the other room and he gets the charts. I said, "Charts? This is interesting." And he says, "Okay, how many volt amps you want?" Bzz, boom. "How much voltage?" Okay, he goes, bzz, boom. "Okay, this is what we need. We'll do this and that and this and that," and he looks through the formula. And I said, "Okay, I see what you're doing now, okay?" Because he's rounding it off. But this has to be matched. You can't round off when they're matched. And the reason is, because then I went to the back and I watched how they're manufactured. They have a thing called pileup. And what pileup is when you wind this bobbin, it's wind on a bobbin lathe. They put,
Yes.
I don't know how many of them on a lathe, 20, 30, whatever the hell it is. And the woman attaches all the wire, and she steps on the pedal and she watches the counter, zing, 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 zing. Well, you don't always get a nice even winding going across the bobbin. Sometimes you're going to get it wind in one place and not in the other, and that changes the length of the wire. You can't change the length of the wire between these two sides. They have to be precisely down to one turn. Otherwise, you don't get an even balance. It leans one way or it leans the other way.
So these two, they have to be balanced, right?
Yeah.
Yes.
What's in the center? Is that the same identical piece, or?
Yeah, it's an EI construction,
Yeah.
which is standard transformer lamination.
So these two, they are identical, but the one in the center.
On this particular
That's
device,
the
all
primary.
three are identical.
Oh, they are all
This
three.
is an isolation transformer.
Yeah.
I made them all three identical so I could get 120 volts out, 120 volts in.
Right.
I didn't step it down at all for 12 volts.
And the number of turns on this, it
They're
has
all
to be
equal.
equal, and it has to be.
Yeah, otherwise you wouldn't be able to.
Yeah.
I wouldn't be able to put the bulb either way. So I spent about 3 years, believe it or not, engineering this to fit any kind of transformer core. You could take this physics and you could go through a manufacturing process and you just change a couple of steps of the manufacturing.
Right.
Nothing really exotic.
Right.
And these always come out the same way every time. And I've built about 200 of them now, and they always come out the same way. Now, this device, if I was to go to a standard transformer guy and have him build this, they'll build this a hell of a lot better than I will, and they'll dip the laminations, which make it even more efficient. But the fact is, I don't have to even measure with a meter. You can measure it with your mind. You can say, look, if it's got enough power to power this light, and then it goes back in power to power this, it's
That
a no-brainer.
shows
It's
you
got to
that
be as efficient as
It's
possible.
efficient as possible.
Yeah, because it's adjustable.
Otherwise, you won't be able to adjust from an AC to a DC.
Exactly. There's no need to even put a meter on it. It's a no-brainer.
Defies the definition of efficiency.
Now, from a commercialization standpoint, when you have a device like this, I'm thinking putting my consumer electronics hat on. In order to, all these electronic, they emit, frequencies
Yeah.
for class EMI, class A, and class B. In scenario you have like this,
Yeah.
do you have any advantage?
I'm glad you mentioned that. I was just going to go there.
Oh,
The
good.
advantage of this is this recycles all of those transients. That's one of the things it does. Because look, if you've got, let's say you got a motor on this side. If you got a motor on this side, you're getting all these transients coming back to here. When you get transients coming back here, this is now generating transients. When it generates the transient spikes on the energy, they reflect back into the device. Well, this is pushing out power, and this is pushing out power. Guess where it goes? It goes to this side. So now you have all that recycled energy. So when you run this on a motor, it makes the motor run more efficient.
What do you
See
mean
what they-
recycle energy? It just
If you ever go to a gas station and somebody's pumping gas and they're going tick, 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 tick,
right.
and you're feeling it in your pump,
yeah,
and you're hearing it, and they're over there going tick, 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 that's called a hammer effect in hydraulics.
right.
In other words, every time it ticks, there's a surge in the energy, in the pressure in the pump. Well, that surge in the pressure of the pump goes all the way back to the pump and pushes against the pump, makes the pump inefficient, wastes energy every time you do that. Well, with this device, when you do that, this is like having an expansion tank. So if you had an expansion tank on that hydraulic system, the expansion tank would take up that pressure every time you did that tick-tick, would take up that pressure and then slowly apply it back. Well, that's what this does with the magnetic field. So you're able to recapture all those transients as they reflect it back.
So if we do
Back
an
in.
EMI scan on this, we won't see
Right.
spikes singing all the way, low
Right.
frequency, high frequency.
The really bizarre thing that I couldn't figure out.
Yeah,
at first.
because I could see application with that because people
Yeah.
in a consumer electronic application they spend a lot of money.
It's a big
to-
problem.
Yeah, in
Yeah.
the Faraday cage and more in consumer electronics, there's not
Shielded,
really
you have to
room
shield it
to
to
shield
shield
Huge.
the
it.
effect.
It's a huge problem.
Yeah.
But this
Parasitic.
is able to collapse so that you don't get the transients. The magnetic field goes like this. And the magnetic field goes over to the other side, so it eats it all up. So all those transients, so this actually works better with a noisy application, works better with a bulb, works better with a pump than a bulb to save energy. It works great with a bulb. It works even better with an LED because an LED wants DC and it makes more transients. And that's why these LEDs get really bright on this. Really cool. So if you hook this up to a computer, all the memory chips and processors are switching on and off, blah, 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 creating transients.
Yes.
The processors and the memory chips actually run cooler. Why? Because they're not bucking against the power all the
Yes.
time. It's collapsing when they need to collapse it. And these actually run cooler. when you run it.
Especially in situation when there are algorithms to put the system into sleep mode, into idle
Yeah,
mode.
that
Those
goes
things,
away.
It goes away.
You don't need all that stuff.
No, I was thinking about it.
So all these companies
Home
that are out
Depot.
there trying to figure out how to make the box go to sleep, how to try to make it wake up in a small amount of time,
Yeah.
this makes them obsolete because this is truly power on demand.
Yes.
Nobody else has power on demand that goes all the way back to the magnetic field. Everybody has power on demand from the switching supply out, and it's all controlled by software.
Yes.
So that stuff is now obsolete. So the interesting part is, we really don't want to be in the power supply business. We want to license this or sell this to somebody. And then they can take it the rest of the way, because there's other stuff we got on the plate that are
Because they
just
can,
as good as this.
they can apply it to their own specific
Yeah.
application.
The challenge we've been having is that when you go to somebody, they say, well, are you a transformer or are you a power supply? They don't understand what the hell they are. So you have to educate them. Well, look, we're not a transformer.
We're not
we're
a
not
power supply. Yes.
But what we are is a reactor.
Yeah.
And what the reactor is a little bit of a transformer, a
Little
little bit
bit
of
of
a
a power
rectifier,
supply.
a little bit of a regulator, which is parts of a power supply.
Yes, yes.
Yeah. So that's the challenge.
But it does the same job, but better.
yeah.
It's just you can classify it. This is a transformer, or this
It's
is a
difficult to
classical
get that point
power
across to
supply.
people. And some of the other uses we thought of using.
I think it's because it shows another paradigm.
It does.
Into power, so that becomes, as I was sitting here when we started looking at this thing, and before you did the switching, and before you actually touched that,
Yeah.
and I said, he's just showing a classical
Yeah, you probably thought this is
electrical
you probably thought
engineering
this is
101
round for
book.
120 and this is round for 12.
That's what I thought. But
That's
when
why I
you
switch 'em.
switched, and then when you touched that, I said, okay, this has nothing to do with those things I was thinking. So
exactly.
now I understand.
That's why I do those. And then in the end, I showed it up, and you see,
Yes, yes.
how the hell does that work?
Yeah, I
Because a
know.
standard transformer should go dead when I do that.
Oh, yeah.
If these were really, this is a 12 volt winding, this is a 120 volt winding, when I short that out, it should go completely dead.
Now,
so it's not damaging when you short this thing out. It's
No,
not going
the
to
flux
damage
goes
your
the other way.
bobbins and coil and stuff.
I have a quick question. I understand the application is broad. There are military, aeronautics, medical, all that stuff.
Oh yeah, think about this for medical.
Medical, yeah.
Tremendous. My patient never has any danger.
Yeah.
You got an isolation transformer, and you don't have that. You know.
Have you taught? Because again, the story is big. I mean, have you planned to maybe put this and package it into one specific to be able to demonstrate to the others? I'm thinking loud here.
Yeah.
I see where you're going.
A classical power strip that Home Depot sells.
Yeah.
Okay, right there, where I have branches for 110 volt AC or suddenly 5 volt DC and all that in the same packaging. That would, definitely, it would catch my attention if I.
Well, that's what I try to do on a tabletop, and I do it this way because this is all open. You can see everything.
Yes. I understand.
You know, you don't know what's in the strip. You don't know if it's got regulators, diodes.
Yeah. No.
But look, I've got everything right here. I mean, this. Look, there's no circuitry, no regulators.
Another question I have.
Go ahead.
How scalable is this? Right now, you say you can get the
because it uses
chip level.
standard transformer parts.
You know, can I use something? Scale it in a situation that I can use it for my house.
Yeah, sure.
Yeah.
You can build transformers in any size. You can build them big enough.
Transmission and distribution we think is a huge market. We can. Did you talk? You mentioned the grid, didn't you?
Yeah, I mentioned the grid, but I'll show you the parts.
So we can scale. We can scale to the largest voltage on the grid and down to the smallest at the neighborhood location, and at the house too.
Here's some of the devices we've built: small ones, big ones. And I got even bigger ones. I got them this big over there. I got one over there that runs a pump that's about that big. So any transformer components that are available, you can use this physics on.
Want me to carry one of those over?
Well, let's get the parts to show. These are the parts that are in the transformer. These are the laminations. They come in all different sizes.
So we can do step down, step up.
See, they put these together inside of a transformer and they go like this.
Right.
And then you just stack another one this way.
And you stack them up.
Yeah, this is the point. They come in all sizes. They call E's and I's. You can get these any size you want. You can get them up to the size of this room. You can build transformers the size of railroad cars with this, and then it's just wire. How reliable is that? And then you take this and you dip it in marine varnish, and the people that make transformers tell us that they guarantee them for 35 years. You can't do that with solid-state components. Imagine the uses where you need DC, and you have to use these big rectification packs. I don't know if you ever seen the big rectifiers. There's as big as this board. They have diode packs. And the problem is they need so much of a ground sink to hook those two because they make so much heat rectifying. This doesn't make any heat rectifying. It supplies the load what it needs.
Now, maybe I'm repeating a question in different ways.
Yeah.
How this work with, you guys are electrical engineers, with phases, like air conditioning.
That's the thing.
Phase 1, phase 2 phases, 4 phases. How does, it comes under scalability of the unit?
Because you can make this in any transformer, standard transformer deviation. Doesn't matter. You can build the transformer to do the multiple phases, because all you're doing is changing the physics of the transformer. So you can change the physics of this transformer or that transformer. Doesn't matter how many phases it is. Anybody that can build transformers can put this physics into a transformer.
Yeah, because
it's physics.
Right now, air condition, obviously, in our house, is that different phase than regular AC light bulb.
It's a dual phase.
Yeah.
So there's two things you can do. You can use two of these and hook them together, or you can make a custom unit that's the same as two of them hooked together.
I have a quick question on this model. If I wanted to get, this is a 12 volt in this case. If I also wanted a 5 volt, what would you need to make?
Good question. I can just hook one LED up to this and it'll light it without burning it up.
thought it wouldn't matter.
It doesn't matter.
Oh.
The magnetic field can completely collapse. So evidence of it, when I short it out, I'm collapsing the magnetic field all the way. That's why I show you that in the end. I short it out.
No, I think what it is, I have different type of a question. Let's say
So I can go any voltage from 0 to 120 out of this device.
Let's say I have a box and I need to provide 5 volt, 12 volt,
Yep.
and 3.3 volt. And these are need to be within, let's say, 1%.
Yep.
That's your ATX box that we built. That was the first thing we ever built. On we have a video of that, and we have an independent lab has verified our savings. We saved 70% of the energy on an 80 plus power supply.
That's great. Now, in order to do this,
Yeah.
do you have to replicate 3 devices individually?
Well, there's a
to
couple
be
of
able
ways. There's a couple of ways you can do it, and it's price sensitive.
Yeah, exactly. Because I'm getting into that. Like if you say one,
If cost is no option,
do it
you
all.
do this.
Yeah.
If cost is no option, you do this. See, this had a 3 volt, 5 volt, 12 volt device, and then the control coils were here. And then I took this and I said, what the hell with this? I don't want to make it specific voltages. Let's make one device that does all the voltages.
Right.
So that's what this is. So you can do it either way. It doesn't matter.
Can you do this with that?
Yeah.
You could
sure
be
you
able
can.
to continuous.
Sure you can. Yeah.
Do you need to put another glue logic in order to make sure my chip is getting 3.3 volts?
No,
No, he just creates it from there.
it creates it from here.
There
It
is-
pushes
there
back
is
on the
no
field.
other thing. There is no regulator.
No
needed.
regulator.
So we call it power and demand. Really, it's the load is telling the transformer how much energy it needs to
See,
react.
that's why I do this. Look, shorting it out. See? You know, it means I can go 0 to 120 volts out of these terminals, and I can still touch it.
Yeah.
You know, if I can short it out, it's going 0. But I can put one LED on there and it'll light it up. Easy. Anything up to 120 volts. Now, if you need more than 120 volts, fine. You don't make it an isolation transformer. You make it a step-up transformer.
Yes, yes.
Make it a 1200 volt output. And then you could really step up to any voltage you want. So you make this to the highest voltage you want out of it.
Yeah.
Can you speculate on the what energy? I know you don't like the word savings necessarily, but the increased efficiency in a home, if it were that sitting at the wall. Do you feel like speculating there?
It's hard to say because all the different appliances have different transients that come from them. But evidence of efficiency is a no-brainer because look, if you can power this and you go from this to that, you don't need to ever measure it. You know that this is as efficient as physically possible. It has to be because if it can automatically scale down to what this needs from here, you don't ever have to go to reading it. It's a no-brainer.
So you're saying there'd be greater efficiency for the whole house.
It has to be maximum efficiency because you can't go from a 120 volt load to a 12 volt load without saving power. You see? You can't. It's a no-brainer. It's easy to understand in your head. Well, if this device only puts out what this 12 volt device needs, and then can go up to what this 120 volt one needs, then it's only going to put out the power that's necessary. Bottom line.
Well, you can see I'm making the case for putting this at the front end of the house
Yeah.
connection.
And once you know that, you don't have to measure it. You know.
I understand. You know, to play devil advocate in here, you could show it. Yeah, I mean, it's no-brainer.
Yeah.
Is there any way that you could really quantify the efficiency? You say, I mean, is there any...
Yes, there is. I've done it. It's very hard to do, though.
It's hard to do.
Very hard to do.
Except for our first unit, which was easy to do.
The first unit was like this. It's easy to do with this. But this has control coils and this has measurement points.
Yeah.
You can do it easily with this because this is customized electronics. Whereas this one's so automatic, you can't do it.
So, okay.
I'll tell you how I did it. You take a 120 volt source, and you take an LED, and then you put a switching power supply on it, and you measure these LEDs with a light meter.
Yeah.
This is how much light you have, this is how much power it takes. Then you take the same thing and you put it on this device, and you find out that this thing uses a third of the power for the same amount of light. But the problem is that people that see that experiment say, well, okay, I know what that is now, but let's say we go to a better switching power supply, what's going to happen, okay? So it becomes a pissing contest.
Yeah.
And I don't want to have a pissing contest. So now, when I can go from here to here, I don't have that pissing contest because now They know in their head, well, if this thing can go down to this voltage or up to this voltage, it's only putting out as much power as needed. I eliminate
Edison
like
and
this.
Tesla should have been here.
Say again?
Edison and Tesla should have been here.
Yeah. Well, we had a comment early in our development cycle where someone said the early guys, if they had gone this is the way they should have gone. This technology would
Yes.
changed all electronics for 100 years.
Yes, yes.
So we just went back to Tesla and
Yeah.
picked up where they left off.
You basically, as I was thinking, you basically went back to Tesla's coil concept,
Yeah.
and you can. I understand.
So,
So you see how you don't have to, you see how this is the whole test.
Yes.
Yeah.
This is about as simple a test as you can get. This, if I can go from here to here, I don't ever have to put a meter on it because I know the thing is only supplying what's needed, no more.
Now, who would be your end user? I mean,
Oh my
kind of. I understand it's very scope, but we gotta put
It's
kind
easier
of
for me to
our
tell you who
arm.
wouldn't be my end user.
Yeah, who cannot be actually. But I want to kind of see if we can really articulate, put our arm around this rather than be too general. For example, Edison, a power plant company, Edison could be a client.
Yeah, absolutely.
How could be Edison be a,
Well,
because that's the source that bring power to the house.
Yeah.
How could Edison, I'm saying Edison, power company,
Yeah.
power distribution company per
I'll just
se
tell you
could-
one of the challenges they have, and there's many that they have. They generate power at a central point. There's a centralized power. At the end of the branch, they have a huge power drop because of the resistance of the wire and the transformers. So what they do is they do variable size wire to distribute the power. They'll start out with a very small wire with a very high voltage on the big run. And off of that, they'll run all these little branches. And what these little branches do is little distribution points. And they take it and they step up the step down the voltage, step up the current for the little branches. Okay. The problem is the guy way down the end has to be guaranteed 120 volts. So they have to distribute it at a very high
So you
voltage
see all
for a
those
little
things
current.
up there.
Yeah. So what this does is, if you hang two grids on it, it's always going to have the same voltage. It's going to balance itself out. So you got in the morning you got the industrial power firing up. A little bit later you got the residential powering up. It's always going to balance itself. The way they do it now, they have these balancing stations. And what they do is when they combine two grids, when they cross, they take it off the grid, they charge a battery. Now when the other grid sags, they go from the battery to an up converter to that grid. Well, you don't need to ever do that. You don't need to go to batteries for storage and back up again, because now this only supplies what's needed. So you're not creating heat in the distribution transformers and wasting it. You're only powering the houses up with what they needed. Right now, 99% of the power is wasted from point of generation to the house. 99% of it's just wasted down the toilet. You don't get any of that waste with this.
So what you do? You have to something similar at the house.
Well, now if you took this and you put it out at the substations, you could balance all the grid processes with this device. You know, because
In a
right now
larger scale.
they got all this cooling systems and all this crap going on, and they soak them in oil and all these other things to get rid of the heat in the distribution cycle. You don't have the heat with this. You don't have the buckling. You don't have the safety problem. You know, a guy told me one time, he says, this is a fireman, used to be the chief of the fire department. He said, the worst fire we have is a transformer fire. I said, really, why? He says, well, you got all those oils and that heat, and you don't know what the hell's going to happen. You don't know what's going to happen. It's completely unpredictable when a transformer blows up. Well, this thing doesn't generate any heat. There's no back EMF. All the power that goes through here is reflected to the load.
Question. When this scenario that you have in here came about, it was this year, 2009, 2008. Where was the time that you really came up and really came, to a situation that you could demo something like this?
Well, it was a long, hard road. The first time when I came up with this idea, I thought, I'll tell you about it. I was working on a software product, and I had all these servers running. They were all running fans. And I said, shit, if I could just get rid of the fans in the computer, I'd be happy because it was like a wind tunnel. And I said, this is too much noise. So I went over and I looked at the Intel spec, and I seen 3 volts, and I seen all these little square waves. 5 volts, all these little square waves. 12 volts, all these little square waves. And I looked really close at it, and I said, you know, the one thing is, none of these square waves match up at the same time. And I said, well, this is really interesting, because in between the square waves is wasted power when the power supply has to have the power available, because you don't know when the demand is going to come about. So, of course, it makes sense that you're not going to need 5 when you need 12 and 3. So I said, if I could come up with a device that could supply the power only when needed and go to sleep the rest of the time, like the problem you're having with set-top boxes. I was trying to solve the set-top box on a basic physics. I started thinking, and I said, gee, you know what? I can remember when I was a kid, my dad took me to the construction site, and he said, see that thing over there? I said, yeah. That's a generator, okay? I want you to keep gas in it and keep that running. Because if that thing goes off, I'm going to kick your ass. What? He said, well, look, the guy's got to drill, they got to cut, they got to this, they got to have power when they need it, okay? You can't turn that thing on and off. It's got to be ready. So it's your ass if it goes off, okay? All right, fine. So my job was to keep that thing running that day, right? So I started thinking about that, and I said, gee, you know, today we got cordless drills, cordless saws. Everything would be cordless now. And I said, if I could do that with a computer and make it work like a cordless device, it's really like power on demand. You take the power from the battery when you need it, and then you charge it up when you do. So if I could make that happen in a computer, I'd have a hell of a product.
When that time was?
Oh, this is probably 2005, maybe?
2005.
Yeah.
2007.
No, it was earlier than that. It was down, no, 8. Anyways, so I was thinking about this.
How
and it took a
different?
while.
Were you on your own, or you're working for a company in that time?
No, I was on my
He's
own.
working for me.
Yeah, I was working for you, yeah.
It's a joke. It's a joke. We're partners.
So
How
I started
difficult is this construction of these coils?
thinking, easy as hell.
It's easy.
Yeah.
Let me finish with
Same
this.
construction as a standard
Because
transformer.
now, what you see here, let's say 2008.
Yeah.
I mean, just for us
2008 you started this. Was
to
this.
start it.
So I
When
thought
you
back-
came up with this scenario, because most of the stuff I worked with you guys in past in 2009 is developed all these
Yeah.
bobbins. You got at times you got rid of bobbins. You went to like a printed circuit board and all those things. But this is the one. This is the first time. I mean, obviously I see this.
Yeah.
When you came, you came timing on this.
Well, the first one, let's see how it evolved. The first one, and I started thinking after I thought of that, I said, you know, the part in the power supply that nobody's really refined is the transformer. I started looking at a switching power supply, thinking how I could turn it on and off. And I looked at it and I seen nobody's doing anything with the transformer. Nothing. It just sits there and uses power. I said, if I could come up with a transformer that turns on and off, that would solve my needs. And I could worry about the rectification and regular rectification. So I went back in time and mind, and I thought about something I seen in school, which is called a mag amp. And we taught us about a mag amp. A mag amp was invented by the Russians. And it was basically a transformer you could turn on and off. And it was the predecessor of the transistor. It was a way of controlling high current applications with magnetic fields, like a transistor does. And they could move, it was invented for moving gun turrets. They wanted to move a gun turret with a motor, and they wanted to control it with a very small switch, or rheostat. So that Russians invented a thing called a mag amp. So I took the basic mag amp design, and I said, okay, how can I make that respond to the circuit? So I constructed a little load, and I took that load and I controlled the mag amp with the load, and the load was nothing more than a resistor, load resistor. So I could watch the load go into the computer, what it would demand, and I could turn the mag amp on and off. But it was a little wasteful there, because I was always monitoring the current through a load resistor to see how to turn the mag amp on and off, and that was the early model. And I said, how can I eliminate that? And then I started thinking about the physics of what the hell was going on. And then I realized I could take the load resistor, or the sensing coil, the control coils, and I can wind them into the secondaries if I can control the whole physics. If I just think about this in terms of physics, not electronic engineering, I can incorporate everything. So that's what I did. I started going from a mag amp to just modifying the physics. And that's when I came up with this unit. And the only reason I build it like this, rather than, I can build it in planar, and I can build it in toroid, it's just changing the physics, not the components. I know how to build them into all the different components, and I've got all 3 of them patented now and issued.
Oh, wait a minute. I thought you said there is no patent on.
There's 3 patents on this. This is the old stuff I'm showing you. I got the new stuff I'm going to show you too.
Okay.
So there's 3 patents issued on this.
It's already.
Right there on the wall.
Oh, okay. Now those 3 patents, I mean, it's a part of this. Is the whole thing?
Well,
or?
one of the patents is on the basic method of how to do this. That's a method patent. And the method patent, because the new patent laws, has to have an apparatus with it to show how to work the method. Because you can't just patent a good idea. You can't say, well, I got an idea for this, and I just want to write a patent. They don't allow that.
Yeah.
They say, this is what you got to do, and this is how you do it.
Yeah.
So you have to have method and apparatus. So the method and apparatus is bobbins and coils is the first one. Then we have another patent on planar. Then we have another patent on the toll ray application.
When those patents were issued?
I don't know, what's the date on those?
10, 11, 12.
Oh, okay.
Yeah. So we got everything covered on this and how to do it.
So this was those 3 patents is issued after.
Our first.
Yeah, because I
first
was
meeting,
working with you on 2009,
Yeah.
and you were working on those, and those 3 is already issued for you guys.
Mhm.
Now, what are you? What's the pattern in here? Do you combining all this? So what's the?
No, you have a method patent. That's the
Yeah.
basic. That's not the basic science, but the basic how you derive this
Concept.
using the
Yeah.
science. Then you have the bobbins and coils rolled into that.
Yeah.
Then, because planar would be more than 20% difference, which means somebody could apply for a whole new patent and just name us as prior art, we had to cover planar.
Right.
We just had to. Okay, so we got a planar patent. And then because toroid is more than 20% different than bobbin coils, we had to get a patent on that. So that's the whole family. That's every way everybody knows how to make a transformer now is covered in this methodology.
So the new patent you're gonna apply for another patent. That's why your the conversation was
It's a
that.
different project.
Oh, this is the project.
Yeah.
Okay.
I'm updating on your old stuff.
Okay. All right. Now, that's good.
I call this old stuff.
By the way, congratulations on all
Thank
those
you.
3 patents.
Thank
You
you
know,
very
because that shows. I mean, among us, we got a couple dozen patents.
Can I get the numbers?
Sure, they're online. Just look up Richard.
Oh, okay.
Yeah. Now, we kind of
Last name?
now, in a power supply industry, we have a switcher power supply and we have a linear supply.
Yeah.
And there are reasons we have linear supplies because it's cleaner and for instrumentation and stuff. What does your invention here does between linear and power switcher? Are they just discard them completely, or
Yeah.
a switcher power supply?
This is a hybrid between the two.
Okay.
It
So
does
this
everything-
is somewhere between.
Yeah, this does everything the linear does in a linear fashion, and everything the switcher does in a magnetic field.
Okay.
So instead of using discrete components, it just uses magnetic fields to do what a switcher can do. So these are all great questions.
Yeah.
The challenge is we don't want to be in the power supply business. We don't want to be in the transformer business. It's time to license or sell this thing off.
Yeah,
Those
exactly.
guys probably hate this. So.
They hate it. They look at it and they say, "Oh my God, this is a challenge to my job."
Yeah.
You know, we've gone to several
It's
power supply.
conflict of.
We've gone to several power supply companies and they look at it and they think about it and they say, "Oh Jesus, we're going to be out of the power supply business when this thing hits the market," because you know the people that design power supplies are really in the business of engineering what? They engineering rectification, regulation, capacity.
Put all this together and make money.
No,
Yeah.
obviously.
They go away when this thing hits
Yeah.
the market.
Usually, all these power supply there are a few big ones, and then there are little guys,
Yeah,
right?
and this is a game changer.
Yeah.
Well,
What was your
the giant power supply
Yeah.
companies that control the world?
so far? How did you guys approach this with all these?
We went to one or two. We went to a company that designs hardware, that buys switching power supplies, and we said, we got this great new thing. Well, they thought we were in the power supply business. They said, okay, we'll give you a switch. You make one to fit in our switch. We made one to fit in this switch, And I made it to the exact current level of that switch, which was 3 amps at the time. And I brought it up to them, and I brought just the power supply up to them. And they plugged us into one that wanted 5 amps. And it burned it up. It wasn't made to go 5 amps. It was made to go 3 amps.
Oh.
So it was too much of a load, so the wires were too thin. I put small wire. I made a small one. I made a little tiny one to fit inside their switch. And I want to make a tiny one, I had to use tiny wires. Okay. Well, they were drawing more current than I could supply, and it was past the fusion point of the wires, and the wires burned up. And I said, but don't you guys understand? This is a method. This is a device. We're not trying to sell you a power supply. We're trying to demonstrate the concept to you. You can say
they didn't understand what you were.
They didn't understand what the hell we were doing.
And we were not as refined as we are now, too. We had a different design. It'd be a piece of cake right now.
I tried to make it very small, but these guys. So I said, "What do you guys understand about power supplies? How do you test power supplies?" Oh, here's what we do. We take it, we plug it in, and we put the current meter on it. And if it doesn't smoke, it's a good power supply. We just give it the smoke test. That's it. We don't know anything about power supplies. We don't want to know anything about power supplies.
They look at it as a black box. Power
It's
in,
a black
power
box.
out, and what if it supplies enough juice to run there.
So we went through that exercise a couple of times. And everybody said the same thing. We don't know anything about power supplies, and we don't want to know anything about power supplies.
They look at it as a black box.
Yeah. So then we went to the power supply guys. And the power supply guys were seriously threatened by this. All the engineers were basically like, we don't want to see that. It's like, we don't want to see that damn thing. Because we realize when this thing comes out, their jobs are gone. What are they going to regulate? What are they going to design? There's nothing to design. This can be made by a transformer company. There's nothing to engineer anymore. There's no components.
Not only that, all those component companies
that
make those components.
When you open a power supply, you know, you look at it, all these hybrid tiny PCBAs soldered to motherboard, and there are a lot of stuff in there.
And you don't even need the regulation or monitoring circuitry that they go like hell to design. What do you need to regulate this for? It regulates itself, manages itself. You don't need to monitor heat. You don't need to monitor voltage. You don't even need to set voltages. All that stuff goes away. This is brain devil's dead simple. If there's any guy that's power supplies that could do this, go from here to here.
Yeah, that's more than enough.
Imagine what they'd have to do to go from this to this.
Yeah.
You'd have to switch something manually. That's a software trick and a hardware trick and a lot of circuitry.
You need a lot of electronics to be able to switch back and forth.
Yeah.
You need solid state relay. Who knows?
Yeah.
What else you need?
It would be a headache to do that.
Yeah.
Yeah, you can see there's nothing under there.
Show it to the camera.
We just taped up at the bottom.
Okay, basically,
Because the wires connect right to here.
I don't see any resistor, capacitor.
No, there's nothing. No diodes, nothing. I can put a scope on it, and you'll see that this is a sine wave. Pure sine wave comes out of here. And you'll see the sine wave collapses when I put this in.
Richard, how's the 12 volt coming here? Is it clean? Is it noisy? You know,
It follows exactly the pattern of the diode. In other words, when I hook a red diode up, it has one frequency. When I hook a blue one up, it has one frequency. When I hook a green one, it has another frequency.
Okay.
So it's completely reactive to the load, which is really cool to watch. I had a guy come in one day and he says, "Can I hook a scope up to it?" I said, "Sure, go ahead." And he hooked the scope up to it and he did the thing with the lights and everything. He said, "God, I've never seen anything like this." I said, "Well, it's doing what I told you. It's just collapsing based on what you put on it, what load you put on it." So what was really interesting was I found that it actually changes the frequency of the magnetic field based on the color of the LED, which is really cool.
I mean, this is really awesome. I'm kind of surprised, up to date, you have not been able to get someone really, people lined up behind the door.
Well, we've had people lined up and they haven't closed. That's the challenge.
The trouble is, you know what happens is we get them all excited about this, and then they start thinking in their mind, they're thinking, okay, how can we broker a deal with this? That's what they think. They say, rather than us buying it or using it, think of all the companies I could sell this to. And then this becomes a different deal. And then they try to manipulate and control us. So what we need is help of somebody who can take us to the right connections, show this to a company and say, here it is.
No,
and get a commission on the deal. We pay somebody a commission to do that.
Right. I mean, you are trying to license this to. I mean, there are a couple of ways.
Our first desire is to sell it, really.
Yeah.
Because there's other things we want to do, and you know, we're not getting any younger, and the other things are just as complicated as this, and just as good as this. So it's time to see this thing go.
Yeah.
Set it off on its own flight.
I see.
Yeah.
That's the best of all worlds.
So we have different business models. We could do market segments like the grid. Someone could have the control of the grid or the power supply for certain levels of voltage and amps. Also motors is a huge user of electricity. We recently have been experimenting with motors and find a significant energy savings. And we could even do a bolt-on unit to many of the old motors and change them. Ideally, you would have all the new motors would be built according to these using this technology. So there's lots of ways to go. One is to market segment, one is to sell the whole thing and let somebody else do all that. So the major players, the billion-dollar electronic companies, are the guys who could take this over and really optimize it.
The question is, Robert, if you had $2 million today, right? Someone come give you $2 million to develop this further. Would you have done something different right now? You've been thinking about it for the last 4 or 5 years, and you say, okay, obviously money, and there are many ways you can skin the cat, present this, and you know all those things, and really, I'm pretty sure what it boils down to the money and how much you want to spend.